Why does your coffee mug never show a clean double-slit interference pattern? What if quantum rules never switched off? In the energy filament theory, decoherence doesn't kill the quantum. It pushes the phase order of a local coherence envelope into the energy sea and environment until the fine timing becomes unreadable. Textbooks often summarize this as aw-funk diagonal terms decay, which is correct and also feels like explaining a movie by listing file sizes. The visual is closer to a 4000 wallpaper being sanded into a blurry mosaic. The energy is still there, but the crisp phase relationships that make dark-unk bright stripes are no longer aligned. In this picture, the environment is not a quiet stage backdrop. It is a gigantic recording device made of air molecules, thermal photons, lattice vibrations, stray fields, cable noise, and microscopic defects. Each tiny interaction steals a little which path detail, not by magical spying, but by simple physics. If the world can respond differently to two paths, it can store that difference somewhere, and once the difference is copied into many degrees of freedom, it stops being something you can recombine. Think of tearing a photo into confetti and tossing it into a windy city. Nothing supernatural happened to the photo. You just scattered the information into too many places to recover. That is why decoherence can happen without meaningful energy loss. A system can keep almost the same energy while losing its ability to interfere, because interference lives in phase order, not in the energy meter. This also explains why big objects are classical is the wrong lesson. Big objects are still quantum, but they are constantly leaking phase details because they touch everything. A dust grain has billions of internal vibrational modes. It emits and absorbs infrared photons. It bumps into gas. It carries electric patches and polarizes its surroundings. So it's like trying to keep a marching band perfectly in step while a stadium crowd keeps bumping them and recording from every angle. The beat doesn't vanish, it gets scrambled. If you work extremely hard to isolate that dust grain, cool it, shield it, and control its leakage, coherence comes back. That's not philosophy, it's what echo and dynamic decoupling tricks do in qubits, and what quantum eraser-style experiments show in optics. They don't resurrect dead quantum laws, they just undid a small part of the environmental record, so the phase order becomes readable again in a controlled subset of data. Here's the deeper twist. The energy sea is not perfectly still even in a vacuum. There is always a baseline jitter in tension and texture. That background roughens phase like tiny waves wobbling a boat's timing. Add multi-unk channel coupling on top of that, and the system is pushed toward the states that survive best. Those are the famous pointer states. In this language, pointer states are corridors of minimal disturbance, patterns that don't get ripped apart by the environment's constant copying. And that is why classical trajectories look so stubbornly stable. They are not the only real states, they are the least fragile lanes under real-world noise. One more caution, decoherence explains why superpositions become unobservable locally. It does not, by itself, explain why you get one definite click instead of a fuzzy half-click. To get a counted event, you still need the measurement chain, coupling, closure, and memory. Coupling ties the system to a readable device. Closure is the irreversible latch that produces a single outcome. Memory is the amplification that spreads that latches into the world so it becomes history. So the punchline is simple. Quantum didn't disappear, your phase resolution did. Next time, we'll push this into a sharper rule and ask why asking more precisely always costs you somewhere else. Tap follow, share it on New Physics, Clear Universe.